Thank you very much. Multi-threaded JavaScript. It doesn't entirely cover what I'm going to talk about, but it's definitely a big part of it. So these are my slides. You know, if you make your own editor, you can have your own slide stuff. 4 years ago, I decided to try to redo everything you see in a browser using WebGL. Draw everything, and things like an editor or split panes or these kind of things. Can you do them in WebGL? Because WebGL is high performance, but the API is incredibly tedious and bad, right? And it is that because it's very, very low level. And many of us go like, what is actually low level and what is high level? Well, low level generally means that you talk to the machine in a more primitive way than, you say, draw a circle. That's not a thing the computer can understand. You have to tell the GPU to take some geometry and transform it to the screen and fill it with some kind of pixel shader. That's low level. High level is, say, draw a circle, right? As web developers, we're very much used to these high-level APIs. HTML is a high-level API, Canvas is a high-level API, but WebGL is really not a high-level API. It's very low-level. That's because it made it in from OpenGL ES, essentially. Is it okay? Yeah. That's because it made it in from GLES2, which is a low-level drawing API that is. I'm hearing this sound go in and out. You want to use the other one? Probably. So I spent the last 4 years trying how to make this low-level API, which exposes enormous amounts of compute available on the GPU, and lift it all the way up to the high level, where we like to say, draw a circle or draw a rect, and then on click, change the color to blue or something like that. So I built about 5 different complete file new, in any dimension, different ways, but still using JavaScript, how to solve this problem. And I want to summarize the things that I learned over the last 4 years before I go dive into where I am today. So, first of all, single character variables are bad. That's something I learned because I wrote one of my first frameworks completely using single character variables. It was quite fun, but I forgot that I was leaning on my short-term memory to understand what I was writing. If I look at it now, I go, you're insane.
You demonstrated it also.
Yeah, it worked.
Yeah.
As long as you remember what it means, then it works. But I was like, why would people type long things? One single character suffices. But you learn and you go, nah. So another thing I realized is that most of UI is a how do I draw things problem. It's essentially how do I make this click turn into that screen. And that means that am I talking to microphone?
You don't need microphone.
They eat them apparently. It's empty. Right.
You don't need microphone.
It was for the video I was thinking. Yeah, we'll need it. Yeah, exactly. Does it work? Yeah. All right. So it's a how do I draw things problem. How do I make interaction? And if you're operating on the screen with shaders, these are the last stage to the screen. It's actually much closer to the screen than HTML. It's running on the GPU. It's the thing that's writing the pixels on your screen. So having that stage be programmable is something new. What can you do with that? And another thing I realized is because I went from single character variables to I'm going to compile my own sublanguage, because everybody was doing TypeScript and all this. I was like, oh, that's cool. I can make my own language. But turns out, unless you really, really have to, it's not necessarily a good idea because you add extra latency in your live coding environment. If you're typing characters, you want the shortest time from you to the program, and if you have to compile tons of things, which is why I'm also not a big fan of compiling ES6 right now, because it takes the nice thing of JavaScript and just throws it out the window. If you're doing that, you might as well transcompile COBOL, right? If you're transcompiling, it doesn't matter what you transcompile. So be patient. That's my only idea for that. So be patient and wait for the web platform to support what you want instead of going to the compiler, because if you start compiling, you lose the niceness that is live development in a browser. Another thing is prototypes are key to performance in JavaScript. I've written a complete UI framework using closure classes. Like you create a function closure and you store all the variables in the closure, and then you return some kind of interface to the closure. It's cool. You're like, oh wow, this is nice because I have actual protection for the variables. But you realize that every time you instance one of those objects, it has to create the closure, which is very, very expensive. Prototypical inheritance is built into JavaScript as the alternative to class structures, and it's a kind of compression algorithm. You can see creating a prototype as sort of like a compile time step. You compile all the properties on the prototype, and then you create an instance which inherits from the prototype to inherit all that execution time for free, right? That's the essence of prototypes. So this is just some of the rants and tweets that you sometimes walk into. You're like, you're wrong, right? So I'm just condensing that to this talk now so that I don't have to do that on Twitter all the time.
Thank you.
So, but it's also, I think, as JavaScript developers, maybe some of the things that may be more applicable to than what I'm going to talk about next, because this is very alien. Also, that GL can be really, really, really fast, but the API is so hard, we need a solution there. Another thing, which is maybe a bit more out there, is that you do not need types, but you can infer them. So in one of my previous attempts, I thought that we needed to add types to JavaScript to make programming the GPU possible, because the GPU does not use var. It uses int and float and vec2 and vec4 and mat4 and all those kinds of types. JavaScript doesn't have them. So how can you sort of fuse the JavaScript space with the GPU space if you don't have types? So one of my previous experiments, I added types because I was like, oh, TypeScript has it right. Everybody is going for types because that's the way to go. But I completely missed the fact that types can be inferred. This is an idea that Haskell uses all the time. And if you do var x is 10, you don't need to tell the compiler that x is an integer. It can see it because you assign something to it. So type inference actually obviates the need to use types. That's another thing that I ran into. Another one is, all those experiments where I just went whole hog into one direction. I'm like, oh, React is great. Take the whole idea space from React and just do it all that way. And then you go, yeah, no. It has some problems when you have to dynamically update the UI and you run into performance problems or garbage collection issues or whatever. So functional definition of UI is great. It reduces your state space enormously, but never limit your users only to that functional space, because then there will not be an answer to many, many problems that you run into. You need to be able to go, okay, all that functional stuff, okay, I'm going to go bypass that for now. So that's like a little condensation of the lessons that I learned, and now I want to get back to Makepad, because Makepad is essentially the thing you see on the screen. It's a WebGL editor, and it has all sorts of nice things. Like I just finished this last week. It has fully working docking, splitting, and you can actually dock fully at the bottom of this thing, right? This is something that Visual Studio doesn't even do. It's like, Visual Studio has these dock arrows, but I think Cloud9 has the right idea. But this is a little extension of that idea, so that you can dock anything anyway. So this is an editor, and this is the code editor of Makepad. And so everything you see here is WebGL. There's no HTML hurt, especially me, in the process. This is a code editor, but it's a new kind of code editor. It's not a text editor, it's an AST editor. So the thing with AST editors, they tried it in the 2000s. A lot of research projects were like, what if instead of text, we added the abstract structure that the compiler uses for the program, right? So the compiler doesn't see these characters. You know, this is a byte array of text. It doesn't see those characters. It uses a tokenizer and a parser to create an abstract tree structure that it can navigate to see what the code says, right? This is like an identifier node, and this is an object literal, and this is a text literal, right? So it has all these structured types. But what are the benefits if you can keep the editor aware of the AST? Well, this has been a long-held belief of mine, and I've tried it many, many times to create it, and I failed every time because the UI framework crumbled under the pressure of trying to build a high-performance text editor. And I think I finally succeeded. Let's see. I need a one-handed UI. So, for instance, I can fold nodes here, and this is using a GPU tweening of the character stream. It's something I would, challenge you to do in CSS. And it can handle enormous amount of text. So this is, for instance, the Makepad application itself. It really doesn't care. The GPU can handle orders of magnitude more information than the CPU because it has orders of magnitude more compute nodes. But so this is an AST editor. So when I'm folding this node, it's not a text operation. I'm operating on the abstract syntax tree of the code. One of the examples, for instance, where I'm headed with this, and this is a very much a work in progress. This is file new 2 months of work. It's probably another 2 to 4 months away from being something that is useful. But let's see if I add my probe operator. So I'm adding probe operators. As you can see, it populates the UI here on the left with the name of the value. So I was really trying very hard to show you that this thing will now be a slider and I can immediately manipulate it. But that didn't make it, so you're going to have to wait for that. But there's plenty to talk about. The nice thing about having the AST in the editor is that all of a sudden I can write code that manipulates the AST. I can fold things, I can use the design direction of this is that visual design tools can manipulate the source that is live reloaded in the application that you're operating on. So visual design tools, sure. Why would you need XML? Every time you talk to somebody like, oh, we need to have markup. No, you don't need markup. It's machine readable. Computers run code. So it's just easier to manipulate than ASTs. But if you put the right level of tooling on it, you can just manipulate ASTs. And in this case, that is the fundamental thought direction of this program, where the visual design tools will be able to manipulate the code. And that's why it's important that it's an AST editor. But you can also do really, really cool things, and I hopefully can show you. So here, you see, by the way, that the editor is tweening. It's actually tweening the entire character buffer. So it can do that on tens of thousands of characters and just tween them into a different shape. But it can do that for this very simple operation. I want to multi-line function arguments, for instance. So let's find something with function arguments. That is an object, but fine. So here you can see that with one new line, I can fold and unfold an object definition, right? Because it's not a character operation. It's an AST operation that just marks for the render engine. Also, I finally settled the tabs versus spaces thing. And the answer is neither. Neither. This editor does not have tabs or spaces. It's all auto-formatted. there is that the concept is gone from the space. It's a great way to win an argument. So, which is also cool because I don't have to sort of navigate with my cursor that empty space that just exists for the visualization. And this puts JavaScript right smack next to Python as to the language, because white space is automatic now. I don't have to worry about it. That also means that it's a little bit less free. So here you see, for instance, the vec2. I'm here. Oh, I'm pressing space. It's not allowing you to, because it's not in the style sheet of the editor. You can enable it and it'll allow you to do it, but it's essentially a hard formatted version of your code that does not that does not have those freedoms. But so the idea of this editor is that it's just not annoying enough that you get pissed off. That's because AST editors are generally like, it ate my new line. Ah, yeah, sorry, my cursor just jumped over here. Yeah, right. So I took enormous amounts of efforts, at least a couple of weeks of trying to do this, to annotate all the white space on the AST. Anyway, this is a whole subject that I can go on for quite a while about. That's actually not where we're going. Because I think I was introduced as multiprocessing architecture. So, what you're looking at here is actually running on 3 JavaScript threads. It's not a single-threaded application. This code editor, if I'm selecting, and if I'm, okay, by the way, check this out. Auto-align object. I don't think I've seen that. Any case. But the idea is that this editor, the whole UI that you see here, is running in Worker. And the UI engine actually builds draw commands that it puts in a typed array and hands off to the main thread. The main thread is the browser as you know it. This is just the thing that has access to all the APIs. But my worker can actually only talk using this message interface. It can say, hey, I have a new command stream for you. So instead of going, hey, we have this DOM tree, which is a C++ abstraction to build, HTML pages, you say, we have command streams. And I can modify those command streams at enormous performance. If I drag this slider here, I actually didn't optimize it yet because it's just so fast. But it's actually regenerating this entire thing. Every single file in this tree is regenerated when I'm dragging the slider. I don't notice it, it's still 60. Yeah, okay. It's still costing. If you do it on a slow PC, you will eventually notice it. But this command stream API is a very nice way to solve how to deal with multi-threading in JavaScript, because there is no way you can manipulate shared state yet. And if you can, it's going to still suck. So the shared state does not exist. All you have is message passing. So what it means is that if you try to do that with object proxying, I tried that, in my previous 5 experiments, I tried to do it with object proxying, and it becomes terrible because you start fighting with the garbage collector. Because if an object in the one thread has to go away, it has to be cleaned up in the other one as well. So you need a much more transactional model if you want to be able to do a multi-threaded approach. So if you look at the source of Makepad, it's actually maybe 10 files that are loaded in the main browser thread, and everything else of the whole application runs in a worker. And this worker approach actually has another benefit, because I don't think I told you what I'm making. I'm making a live coding educational sandbox. So that means that this little thing here, you can just live code. Let me show you a little bit, just tease the performance. So this is 450. This is 4,500. 15,000. Oh. Right? those are visual elements I can click. They have their own animation, their own mouse overs, and I can just manipulate them at this speed. So you have to think about this API as being able to deal with about 15 to 20,000 visual elements in a view, which is what we currently see as a div, really. The nice thing about this, and that's what I was gonna show. So this is a worker. This is a worker that's running. So whatever I do to it, I can, let's say I'm very stupid. I write infinity in a for loop. So I think that's infinity, or is it lowercase? Oh, I think I didn't. It's orange. So anyway, I was going to make a nice visual representation for that, but it actually killed the worker. And I can just close it, and restart it. Oh, it's still on infinity. Oh, close it again. This is a browser surviving an infinite loop, which is not what you can do in the main thread. If I do an infinite loop in the main thread, you're going to have to restart your tab, and your dev tools are going to be dead. It's really horrifying. So this worker architecture actually isolates the processes in a very nice way, and I can start many, many processes. For instance, let's have a buttons example. This is, by the way, doing hundreds of buttons with GPU tweening. I can just dock it here, have parallel processes, isolated, that don't really bite each other except for GPU performance, which isn't really an issue unless you do really stupid things. So this is enabling an actual multi-process application architecture. I can take a piece of my screen and give it to a worker that is isolated and can use it as its own visual representation. Let's see, I have some more. Let's add a tree. This is about 16,000 leaves animating on the GPU, interactively. So this is, by the way, my computer is getting hot, for sure. Right? It's not free. Computation is never free, but you can use it. And if you don't do that, what the tree is doing, it's just going to fire once it renders, and then it's going to be quiet, so it's not going to burn your battery. So I think that satisfied the introduction. But it's an essential part of the architecture. Use workers as the isolates where you run fragments of your program and they talk over messages. Because I need it for this educational environment where you can make typos, you can make infinite loops, and I can recover from them. So, now to the actual hard part, what I spent most of my time on over the past years. How to make the GPU programmable in a way that is easy. How to make it nice. Because the GPU actually only takes giant arrays and things called shaders. There are programs that run on your GPU for the vertex and for the pixels. So the geometry, the position of where it is on the screen has a program, and the pixels have a program. But the programmability of it is using GLSL and WebGL. WebGL is a state API where you say, all right, take all these arrays and use them with these programs and execute. That's what you get. It's very, very abstract and very low level. So, but the thing is programmable. So what about making that programmability accessible? Like for instance here, I make a button that is, let's see, should make this a bit smaller. There's 500 of them or something. And they're all animating in parallel. This is actually a layout. So the way it works is I run the layout and you get your buttons everywhere. And then on click, I just change the size of the button to a bigger size. And then I run the layout engine again. And then what I do is I tween the two states entirely on the GPU. So the JavaScript time for this animation is only 2 layout passes. This is the first one, this is the second one. And everything else is tweened on the GPU, which gives you limitations, but also really cool effects. For instance, this tree, as you can see, minimize zooms. Maybe you can see it, maybe you can. Minimize zooms its elements. So you can use the GPU tweening to do animations that would be prohibitively expensive in JavaScript. The problem is, how do you make this programmable? So let's talk about that for a little bit. I'm going to start very simple. Let's close. Yeah, I have this concept of home tabs that it's not really great yet. Shiny, tiny. Okay. So this is probably one of the simplest pixel shaders that you can write. Here on the left, you see the code, and I'm going to go into the structure of this a little bit more as I go along. Because in order to build a UI, you need higher order structures. You need buttons, you need views, you need mouse events, you need all these things in order to build a UI. You can't just say, well, here's a shader, good luck. So in order to do that, I had to come up with a couple of concepts that I hadn't seen before. Like, if you look at the Canvas API, it has a draw text function, right? Canvas has a draw text function. It has a draw rect and a draw circle and a draw path, and that's about it. All these things are pre-programmed APIs written in C++. But if you move to the programmable GPU for all your rendering, you can do anything you want, really. I mean, not anything you want, but you can do a lot. And it doesn't hold to the constraints of a draw circle, because you can draw anything that you can write a program for that runs on the GPU. So what I've done is I made a new concept called tools, and you can inherit shader classes onto your view nodes. So see the view nodes as divs, rectangular areas on your screen. And you take the shader programs that are written in JavaScript, which I'll show in a little bit, and you can include them onto its canvas. So every view that you see on the screen, like here's a tree, there's a code editor, there's the user program, you can visualize as a canvas. It's just not a pixel canvas, it's a command canvas. Pixel canvases have the downside that if I do this in VR, I'll look at it very closely, I can see pixels, right? If you do this with a command canvas, it's resolution independent. I can show you that this is resolution independent by just pressing zoom. By the way, browser zoom in WebGL, really nice to have. But I'm not rendering an extra single pixel when I'm zooming. I'm just taking in the zoom factor and adjusting my matrices. That's all I'm doing. So it's not a pixel canvas, it's a command canvas, and that means that it's resolution and also orientation independent, because I'm sort of prepping this to run in VR. I want to be able to open this UI on my hand controller, point to something, and then look at it like that, and then the text should still be sharp. It shouldn't be blurry or blocky. Any case, the same goes for this rendering, but I want to show you a little bit about the JavaScript shaders. So shaders are written in GLSL, which looks like C with a little bit of vectors added to it. Means it's typed, means it has semicolons, all these things that I don't like. But it also isn't JavaScript. So that means that if you want to compose these things, you're going to invent templating languages for your strings, PHP. You're going to invent some way to compose these programs out of little bits. And if you do that based on strings, if you put a parentheses wrong in one of the chunks, the whole program is going to be broken, right? It's like generating a tag that's not closed in PHP. It breaks. What's much more solid way to approach it is to have a compiler generate your shader. So at that point, you have to wonder, okay, so what other languages can we express these things? For instance, JavaScript. You could use JavaScript to express whatever GLSL did, or try to. That's the thing I think I have working now. By using type inferencing. And essentially what this does, it takes the glorious toString ability of a function. So the compiler looks at the pixel property of this thing, and it goes, oh, looks like a function. Does toString on it, and throws it into a parser. And then with the resulting AST, I can start to generate GLSL from the JavaScript. This is sort of what Bren and I called the Lisp factor of JavaScript, is that you could do toString on a function. And I have never found that in any other language except for Lisp, where it doesn't actually work as nice. But nobody ever really used it, except for some rare cases. But right now, it's the feature that I'm standing on fully. The ability to take a textual representation of a JavaScript function, compile it, and turn it into something else. In this case, I'm turning this into GLSL. I'm not going to show you the GLSL. If you want to see it, I can turn on dump and you can show it in the browser debugger, because the idea is that the compiler is so good, you're never going to have to look at the GLSL, ideally. But here you see a pixel function. Let me make it a little bit more interesting. So as you see, the code editor actually shows you inline errors as you type, because it's a parsing code editor. It can actually not take broken code very well. So as you can see, you can just animate it with time. Thing is, you can also only animate it with time, because it's a parallel function. It's a pure function. It's executed in parallel for all these pixels. I mean, it isn't really in practice, because I don't have as many CPUs as I have pixels, but conceptually that's how you have to think about it. It's a pure function that determines the color of the pixel that you're looking at. And the cool thing about it is that if you use this way of programming, you can actually draw many things. And I want to show you this tree here. This tree, these lines, I don't know if you've ever built a tree widget, but drawing the lines is terrible, because you have to make all the states into a PNG or something, or do it with canvas chunks, or I don't know how you're going to do it. But here I can write a little program that draws the thing. And I don't know if you can see it, but these are hollow and they tween. So it actually grows the points of the plus and grows them back in. You know, I have no idea how I would otherwise be able to do that if I wouldn't be able to write the visual style of these elements using code. And I can show you that here. This is it. This is the code. So here you have the tools that I use to draw the tree. So I'm trying to use a painter analogy, right? A painter has brushes, but well, he also has a knife. That's not a brush. Okay, so it's a tool. So the painter has tools. And these tools you use to draw your views. And here's the tree line, essentially. You inherit it from something that has a shadow, which is easy, because then I don't have to re-implement the shadowing. Because that's the idea of using shaders in JavaScript, is that you get prototypical inheritance for shaders. If you ever write shaders, you'll notice that's a kind of a big deal. Because you just get text, essentially. You don't get anything. So here's the tree that I'm looking at on the left. And this is the pixel function, and it is like, this is a parallel drawing function. So it runs for every pixel on the lines in the tree. And I tried to make a drawing API that isn't completely terrible. So what you do is you work with distance fields. And distance fields are how I draw almost anything that you see on the screen. It's how I draw the text, how I draw the shapes. Distance fields are functions that you can evaluate for every pixel, and it'll tell you the distance to the shape. It's like a height map of a map. It's a grayscale distance function, and you can write ISO lines, just like on a height map. You can write ISO lines. The outline of this text is essentially an ISO line through the field of the character, And the same goes for this little plus here, or the minus. It's a field that you can compose mathematically, and if you name the functions right, it almost looks like drawing stuff. So here it says, you know, draw this box, or draw this field, and then union that field. And union that field is like merge two shapes. And you can use it. This is actually a very simple function. It's just a min or a max. I keep forgetting. And you can also subtract things. Like here you can see this little box. I subtract the plus from the shape with the mathematical subtract function. And then the resulting field, you can do things with that are vector-like. So you can do you know, like an outline, or you can fill it with a hash, or you can fill it with any kind of thing. Here it just says color solid fill, anti-aliasing function, field, and color. And these colors, all the values that go into this program, are directly programmable from JavaScript. So that's what I wanted to show you in this little example. So here you see a ton of little widgets. You don't need that many actually. Maybe make them a bit bigger. Okay, so these looks kind of nice. They're anti-aliased, have shadows, all these things that you're used to from HTML, but they're totally not HTML. They're totally drawn in a very different way. They're drawn with a pixel function that has all these features. It has a border color, a border width, a border radius, all these variables that you would expect in a C++ drawing engine now live in a prototypically inherited JavaScript chain. And you can specialize the function. For instance, here I specialize the pixel style function. This is just like classical inheritance, where you take a class and you subclass it and you specialize one function. Right? I specialize the pixel function. And then you can say, okay, the border color is a gradient between black and white, and then you get this gradient on the thing. You don't have to, you know, go through a CSS spec committee to get a gradient on a border. It just, you know, trivially added to the library. And I can say the main color is created per pixel. So I can write a fractal, or in this case, I made like a line move over a little function here. Let's see if I can mess with the variables. So I think that about, if you want to know more about this, I can go into more detail. I can do a whole talk for hours about this part. Shaders in JavaScript. So you get the composability of JavaScript with the programmability of the GPU, and the nice thing is you can map data. So that's what I was showing. So GPUs can't really do a lot of things. It doesn't like random functions, for instance. It's really bad at random functions because it does not have any variable input. It does not have state. All random functions have state. GPU doesn't have, unless you explicitly give it a random state. It doesn't have any random state, so it cannot compute a random function. You have to give it to it via a texture or something else, or via JavaScript. In this case, I make a rectangle. I inherit from rectangle, and I give it a call, or whatever I call it. It's like arbitrary. I can name it anything. And then I use that call, or I don't use call, I use color. Yeah, okay. I use the color property, and I use the this. So this does not exist in shaders, right? It's a concept the compiler adds for you. It allows you to pass data into the shader for every draw instance. So here I'm drawing 450 of these things, and every time I generate them, the color is different. Right? I made it redraw on finger down, so every time I click it, it's going to regenerate all those rectangles with a different random number for the color. And all I need to do in the shader is just reference the property on this. So I kind of faked the existence of an object backbone to the shader so you can interact with data. This is really a lot of work. If you look at what kind of stuff you have to do to put this into a shader attribute stream, you're going to be programming for half an hour to just like skew the arrays and add it to all these things. It's really, really terrible. That's what compilers are for. Compilers are for mapping input and output data. How am I doing that time?
3 minutes.
Okay. So, UI architecture, I guess we'll not talk about that then. It works. I mean, it smoothly animates around 60 frames a second. I can do all the things that are incredibly annoying and hard in HTML. So I'm very happy that this time, I think it finally works. It's very React-like. It has a functional, because you can draw everything to a canvas every time, and you can do that with tens of thousands of items. You don't really have to worry too much about maintaining the C++ state. You can just throw up something new. So I already showed the GPU tweening. And now, for my one more thing, got to do that. I'm about 2 weeks away from editing the thing in the thing. Yeah, now my mouse coordinates break. I'm sorry. But, yes, I can edit the thing in the thing in the thing, and I can live code it from the outer entry. So, oh look, it's a file tree. I don't like it white, I want it black. This is about the time it takes for me to boot up my own program. Because it is really restarting everything. So
slow.
I know. How do you live with yourself? Yeah, so I guess that was my 3 minutes. But we covered a lot of ground, and I hope it made some sense. It's very different. So Makepad is a live coding sandbox that I'm going to launch in about 2 to 3 months, hopefully, as an online service where you can live code and prototype and play with the stuff, because the focus is making programming fun. Playing with the web should be easy. Playing with graphics should be easy. And I hope to create something that will inspire the next generation of kids like I was by Quick Basic back in 1992 to just love what you can do with computers. So, thank you.